Welcome to Chapter 12, Heaps and Priority Queues. A heap is a complete binary tree packed into a plain array, and the largest value always sits at the root. To add a value, it bubbles up toward the root. To remove the largest, a new value sifts down until the heap is in order again. That is what powers a priority queue, where you always take the most urgent item next. Let's start with why we need heaps and priority queues. We will look at a simple job that a plain array does slowly, and then see what a heap fixes. Let's look at what you will be able to do by the end of this chapter. First, you will compute parent and child indices by hand, using the simple index formulas. You will trace bubble up and follow a newly inserted value as it climbs toward the root. You will trace heapify down and follow the new root as it sinks back into order. You will check that a heap is still valid after any operation, both its shape and its ordering. And you will explain why building a heap costs only big O of n, using the summed work argument, not a per node guess. This chapter has one main idea, and everything else follows from it. A binary heap is a complete tree stored in an array. The shape is so regular that a simple formula replaces every pointer. There are no left and right fields anywhere. And that is why insert and extract max cost big O of log n, while building a whole heap from scratch costs only big O of n. Imagine you are writing a task scheduler. Jobs arrive in no fixed order, and each one has a priority. The CPU keeps asking the same question: give me the highest priority job to run next. The jobs sit in a plain array like this one. Each number is the priority of a waiting job. The most urgent job here has priority 9. That is the one the CPU wants to run next. The array is unsorted. A new job just goes wherever there is room. The scheduler never asks who is at index 3. It only asks who is the max. This is a priority queue. The only question it ever asks is who is highest priority right now. A normal first in, first out queue is the wrong tool here. We need whoever is most urgent next. One obvious fix is to keep the array unsorted and just scan for the max. Adding a new job stays cheap. You append it at the end, which is big O of 1. But answering who is the max has no shortcut. First you scan and read all n elements. As you go, you track the largest value seen so far. At the end, you remove the winner, the largest one. So one extract scans all n elements. That is big. O of n doing it once is fine. But doing it for every job in the queue is where the trouble starts. Let us predict first. Your scheduler drains a queue of 1,000 jobs. It extracts the max one at a time until the queue is empty. If you scan for the max each time, about how many comparisons does the whole drain cost? Pause and make a guess. A small hint before the reveal. The first extract scans 1,000, the next scans 999, then 998, and so on. Those numbers add up. We total them on the next slide. Now watch it hurt. Extract number k scans the jobs still waiting, which is n minus k plus one of them. Let's add those scans across the whole drain. The top row counts the extracts. Extract 1, then 2, then 3, all the way to n. The bottom row is how many elements each extract scans. The first scans n, the next scans n minus 1, then n minus 2, down to just 1 at the end. Add them all up. N plus n minus 1, and so on down to 1, equals n times n plus 1 over 2. That is about n squared over 2 comparisons, just to drain the queue. Look at the real number. A 1 million job queue drained this way does about 500 billion comparisons. That is half a trillion just to serve a million jobs, and it is quadratic. 10 times the jobs means 100 times the work. We need a better way. The fix is a heap. An unsorted array keeps no order, so finding the max is slow. A sorted array makes the max big O of 1, but then every insert costs big O of n. Each simple array is fast at only one job. The unsorted array, our scan from before, has a cheap insert at big O of 1, but finding the max is big O of n. A sorted array flips this. The max is at the front, so finding it is big O of 1, but each insert is big O of n. A binary heap does both jobs in big O of log, and it is not the best at either one, but it is good at both. Here is the definition to hold on to. A binary heap is a complete binary tree, packed into an array, in which every parent is greater than or equal to its children, so the root is always the max. It gives up full sorted order and keeps only a weaker, cheaper rule, just enough to find the max fast and no more. Both insert and extract max cost big O of log n for a million jobs. That is about 20 steps each, not a million.